on the first question in simple harmonic motion. Very quickly put, it's a simple pendulum that has a mass of m and it's hung by a master string of length n. Now if we slightly disturb this mass from its equilibrium position, will it execute SHM? That is the question. If it does so, also find out the time period for the same. So I have with me Naveen here, who's going to be solving this problem. And how do you think, Naveen, we should be approaching this issue?
Generally, problems of this kind can be solved in two ways. I'll be explaining you both the ways. The first one is the force method and the second one is the energy method. Let's start off with the force method. In force method, first, the most important thing to do is we need to draw the FBD of the given system. The FBD of this mass will be, this is a bob of mass m, the weight will be acting downwards, which is mg, and then there is tension T in the string, which is at an angle theta to the vertical. This FBD is at an angle theta for the system. So next we go on to write the equations of motion for this. Now when you write the components of weight, this is mg cos theta and this component is mg sin theta.
Naveen, tell me this.
Yes.
So we've split up mg into mg cos theta and mg sin theta.
Yes.
Why do we not split up t into t sin theta and t cos theta?
You can do it in either ways, but it's a usual customary to split up mg. So
okay.
So because the torque of T will be 0 when I calculate it about this O, which
okay.
is O here, the point of oscillation.
Okay, but what about m? So mg cos theta will also be 0 as a consequence since it's passing through it?
No, mg will be producing a torque about O. I'll be getting to that next.
So what about its components, mg cos theta and mg sin theta?
Yeah, mg cos theta won't produce any torque about O, but mg sin theta will be producing torque about O.
Okay, alright. So let's continue with the problem.
Yeah. So the torque about O is mg is r bar cross f bar. Now r bar is L bar cross mg bar. Now when you take this is L, this is a vector L, and then this is the vector mg. Now when you take cross product, it goes into the plane of the paper. You use the right hand rule and get the cross product. Into the plane of the paper is in clockwise direction, so we get it as minus mg L sin theta. But torque about O can be written as moment of inertia of the mass about O into alpha, which is the angular acceleration, that is equal to minus mgl sin theta. Now this is the equation of motion for the simple pendulum. From here you can observe the relation between the angular acceleration and the angular position. For it to be in SHM, there should be a linear relationship, but here there is not a linear relationship. So a simple pendulum is not in SHM when the angle theta is very large, but this can be approximated to SHM if theta is small. If theta is small, sin theta can be equated to theta.
When theta is in radians, right?
Yeah, and theta is in radians.
Please don't write this in degrees. It will make the question very, very funny.
So I naught alpha is equal to minus mgl theta. Now we get the linear relationship between angular acceleration and the angular position. So alpha is equal to minus mgl by I naught into theta dot. So from here we get omega square is equal to mgl by I naught.
Okay. So we've calculated omega square and we've calculated alpha.
So
what is the next thing we look at?
So time period, as we know, it is 2 pi by omega. So substitute the omega from the above formula and you get it as 2 pi under root I naught by mgl. From rotational motion we know I naught is ml square.
For a bob at the end of a string,
Yeah.
right? Okay.
So I naught, the I naught is ml square. So
the next step is we substitute these.
we substitute this into the time period and then we get the time period as 2 pi under root ml square by mgl. The m cancels out and 1l cancels out. So time period is 2 pi under root L by G.
The very simple equation we derived, I think, in the 10th class.
Yes.
When this is studied for the first time.
Yes.
Alright, so this is how this equation comes about, guys. So are we done with the question or?
Yeah, we are done with the first method. Let's look at the same problem by, let's look at the solution in a second method.
Okay.
So the second method is called the energy method.
Wait. Will this thing be completed in this? इतने space में लिख लेगा या नया करना है? It's
Can
over.
you scroll down?
No more.
Oh, I think we need to go to the next
Okay,
page.
stop then. We'll do this again. Wait. How to start this here. Alright, so we're back again with the second method for solving this, which is the energy method. Over to you, Naveen.
Yeah, let's start off with the energy method. In this energy method, we need to calculate the potential and kinetic energies of the system, and then from there we get the equation of motion, and from there we can decide if it is in SHM or not, and then we can find the time period from that. So when this pendulum is in equilibrium, it is at this position. So let's say that the potential energy at this height is 0. I'll write P for potential energy and Ke for kinetic energy, and then it is when it is at an angular position theta, it is at a height h from the equilibrium position. So potential energy, as we know, is mgh. Now h is this is L, the length of the string is L minus this height, which is L cos theta. So h is L into 1 minus cos theta. So potential energy is mgl into 1 minus cos theta. And then kinetic energy, which is Ke, will be half mv square. V is the velocity of this bob. So the total energy, as you know, is the sum of potential plus kinetic energies. So we'll be writing that, which is mgl into 1 minus cos theta plus half mv square. As you know, the total energy of this system remains constant because there are no dissipative forces. We'll be differentiating the total energy to get the equation of motion. So differentiating the total energy with respect to time. So d by dt of total energy is equal to m and g are constant, so mg, and L is also constant, L, and cos theta is minus sin theta, so the inner terms become sin theta plus half into m into, this is 2v, and then dv by dt. Here you have
d theta by dt, right?
Yeah. and then there is d theta by dt. So mgl into sine theta into d theta by dt plus the 2 cancels out. V is L into d theta by dt. I will be writing it as theta dot. So V is L theta dot since it is in rotational motion. So I will write d theta by dt as theta dot and dv by dt as theta double dot. So it will be m theta dot theta double dot, and the left hand side will be 0 because the total energy is constant.
Naveen, don't you mean m L theta dot? Because we replace V with L theta dot.
I'm sorry, it's m L square. I'll rewrite this term.
Okay.
I'm sorry, it's m L square theta dot theta double dot.
All right.
And then take out ml. You get g. You can take out even theta dot. It is mg theta dot. Sorry.
We can take out an L as well.
Yeah,
right?
ml. It's g sine theta plus L theta double dot. So this can't be 0. So this has to be 0. So g sine theta plus L theta double dot is 0. Again we use the same approximation which we used in the force method, which is sine theta is approximately equal to theta if theta is small.
So this means what we are solving is always, again guys, remember, for a very very small disturbance from its equilibrium position.
Yes,
if
exactly.
it's a longer displacement, it will not be an SHM, right?
Yes.
Okay.
So it is g theta plus L theta double dot is equal to 0, which implies theta double dot is equal to minus g by L theta. And again from here you get omega, and then time period is 2 pi under root L by g.
Alright, so we solved it using the second method as well, and you can see that both of them lead us to the time period and the equation being 2 pi under root L by g. So let's move on to the next question, Naveen.
Yes,
or is there
sure.
anything else you'd like to say?
I'm done with the first one.
Alright. So after the last question, we are back with another variation of the same. In this case, we have a block of mass m, which is fixed to a massless spring with a spring constant k. So it's a spring this time around and not a string. If it is displaced slightly from the equilibrium position, remember, as we said slightly in the last question as well, this is also a small disturbance. Does the system perform SHM? That is the question. And if it does so, find the time period. So Naveen, what do you say we do about this question?
As we have done in the last question, we can solve it by two methods again. Any SHM question can be solved using two methods. So let's get with the force method first. So as I have already told you, we need to draw the FBD. So this is the block of mass m, and there is this weight acting downwards, which is mg, and then there is force kx upwards. So first let me explain you about which point it executes the SHM. It executes SHM about equilibrium position, as we know, but equilibrium position is not at the natural length of the spring, but it is at a length of natural length L plus another delta L, because after you attach mass to the spring extends by a length delta L to for the mass, to accommodate for the mass. So it executes SHM about this position, which is at L plus delta L. So in equilibrium position, K times delta L is equal to mg, because spring force will be cancelling out the weight in the equilibrium position.
Okay.
And when it is at rest, obviously. So this is the first equation, and then this is at equilibrium position. Now if you displace this mass slightly from the equilibrium position, we need to see if it executes SHM. So now it is slightly displaced. So the resultant force acting will be F is equal to mg minus k into the elongation, which is mg by k plus x. X is the displacement from the equilibrium position. So
that we've created?
Yeah.
Okay.
So the total elongation of the spring will be delta L plus x. The delta L is mg by k from the first equation. So we get mg minus kx. So mg and mg cancels out, from where we get minus kx. So F, which is ma, is minus kx. A is the acceleration of the body, x is the linear displacement as I have shown in the figure. So A is equal to minus k by m into x. So from here you get omega square as k by m, which implies omega is under root k by m. So time period is again 2 pi by omega, implies 2 pi under root m by k. So we got the time period of this system by using force method.
Okay. So now that we're done with this, and as you've seen, this is a very quick solution of the problem, let us try and solve it using the next problem. Or well, the next method. The problem remains the same. So we're back with the second method to solve this question, which is the energy method. So Naveen, let's get it started.
Yes. Let's start off the energy method for the spring block system in vertical direction. So the first thing which you have to do in this is write down the energies, which are potential and the kinetic energies of the system. First, let's write the potential energy of the system. As I have already said, this is the equilibrium position, which is at a distance L plus delta L from the point of this topmost point of the spring. So it executes SHM at this height. So let's say that potential energy is 0 at this equilibrium position. So if you move the block by a distance x from this equilibrium position, let's write potential energy at this position. So the potential energy will be half kx square for this motion from the equilibrium position to a position x, plus k times delta L into x, because there is already spring force of k delta L acting on this body. So even that will be counted into the potential energy, which is k delta L into x, and then minus the gravitational potential energy, which is mg delta L, which is
mg into x, right?
mg into x. So from the equilibrium which we got from the force method, k times delta L is mg. So
where did we derived this in the last question?
Yeah, we derived this in the force method.
So if somebody wants to solve it only using the energy method,
Yeah.
How can he do it directly without drawing upon things which are done in the force method?
I'll give a small tip at the end of this question how to do that, because generally in questions of this type you don't need to write this extra delta L term. The potential energy can be directly written as half kx square. That is what we'll be getting by solving this.
Okay.
So this extra delta L won't be forcing the potential energy term.
Okay, so we won't really be using the delta L when we are using the energy method, but we'll use it in the other method.
Yeah, exactly.
Okay, alright.
But just this is the first problem, so I am showing in a more detailed way by including the delta L also.
Alright, so we need to understand the concepts because before we can take shortcuts.
Exactly.
Okay.
So K delta L times X is mgx. So the potential energy will be half kx square. So this is what I have told before. This delta L term won't affect the potential energy. And then the kinetic energy. Say the velocity of the block is v at this position. So kinetic energy, as you know, is half m v square. So the total energy is the sum of potential and kinetic energies, which is half k x square plus half m v square.
Alright.
So again differentiating it with respect to time.
So another thing we should point out, when we differentiate it with respect to time, the reason one side, which is differentiating total energy with respect to time, becomes zero is because the total energy is a constant. It will remain a constant of the system regardless of the time, and which is why we equate it to zero.
Exactly.
Right? Okay.
Since there are no dissipative forces, there won't be any loss of mechanical energy from the system.
From the system, exactly. And that is the theory behind why we equate the entire equations to zero. Because if we just equate PE to zero or KE to zero, on differentiating it with time, we will get a wrong answer or we won't even get an answer.
We won't even get an answer.
Exactly. So let's move on.
So d by dt of total energy is K into half into K into 2x into dx by dt plus half into m into 2v into dv by dt. So dx by dt, as you know, is velocity and dv by dt is acceleration, and then the two cancels out.
Okay.
So the equation reduces as kx into v plus mva, which is 0.
So
you can take out, you can remove the v term and then you get the same equation of motion, that is kx plus ma is equal to 0, which you got from the force method, and then omega is equal to under root k by m, from which you can get the time period as 2 pi under root m by k.
Alright, so we solved the same problem using another method. I hope both of you are, I hope all of you are now comfortable with both the methods and can solve any kind of an SHM problem that comes up using either of the methods that are required at that point of time.